Welcome to the next video lecture of real analysis. So the last class, last video uh, we have seen an ordered set which contains a subset which is bounded above. Moreover, it has upper bounds but no supremum, and set having lower bounds but no infimum. So if in an ordered set, if every subset, every non-empty subset which is bounded above, um, that means every subset, a non-empty subset which has upper bounds, then if it has supremum, always every non-empty subset which is bounded above supremum, then we call that as least upper bound property. So we shall define. It says, so let s comma less than be an ordered set. S is said to have least upper bound property, least upper bound property, that is LUBP, least upper bound property, if every non-empty subset of S which is bounded above, which is bounded above as supremum in yes. So it says every subset of yes, with a non-empty subset, every non-empty subset of S which is bounded above as supremum, then S is said to have least upper bound, or S is said to have least upper bound property if every non-empty subset of S which is bounded above has supremum in yes. Similarly, if every non-empty subset S is said to have, okay, S is said to have greatest lower bound property, that in short it is GLBP, greatest lower bound property, if every subset, every non-empty subset of yes which is bounded below, has infimum in yes, as infimum in yes. So by this definition, it is easy to understand that my Q, that is set of all rationals. So we have seen A and B are two subset of Q in the last video, such that A is bounded above and B is bounded below, and A has no supremum behind, no infimum. Therefore Q has no least upper bound property, as and also greatest lower bound property. Q has no least upper bound property as well as greatest lower bound property. Okay, now we shall see one useful and very nice result in this section, that is so let S comma less than be an ordered set, then this yes this S, this okay, we need not to mention this ordered field, it's already mentioned. So then S has least upper bound property if and only if it has a greatest lower bound property. That is, in an ordered field, if the S has least upper bound property, then it always has greatest lower bound property. In other words, if it is greatest lower bound property, then it has least upper bound property. That's if and only if condition. Now we shall see the proof of this result. Okay, so we shall go by the assumption. Suppose, assume that S has least upper bound property. Now, S has least upper bound property. That means every non-empty subset of S, every non-empty subset of S which is bounded above has supremum. Now we need to show S has greatest lower bound property. Now, to show S has greatest lower bound property, we need to show that every subset of S which is bounded below has infimum. Every non-empty subset of S which is bounded below has infimum. Now let's consider a set. Let E be a subset of S which is bounded below. In yes. Now say now S is an ordered set, so it's not mentioned whether it is an R or Q. I don't know. It's just a set. Imagine my E is a subset of S. Say this is my E. Say this box represents E. And we don't know how it looks like. Say this box is E. Say this box is now E. Now it says this box is bounded below. So don't worry about this line. Just worry just about this. Now this E is bounded below. Say which is bounded below. That is if I take if F is a if F be the not if let F be the set of all lower bounds of E. Set of all lower bounds of E in yes. So this is F. Let if I consider a set F as the set of all lower bounds of E. Now E is a subset of S, which E is a non-empty subset of S. Which is bounded below. Therefore my F is clearly not equal to empty, because suppose F is empty means my E has no lower bound, but it's not possible because we assumed that E is a subset of S which is bounded below, though, so E has lower bounds. Therefore my F set is not equal to empty. Now so for any F belongs to F, now F is the set of all lower bounds of E. So this F is a lower bound of E, that is F is less than or equal to E for all E belongs to E. Now in other words F is less than or equal to E. So every element of F is a lower bound. So F is less than or equal to E for all F belongs to F. For all F belongs to yes. This implies now if you restrict this E, then and for every F belongs to F, for every element of F, E is greater than or equal to F. This implies this E is an upper bound of F in S. Now observe in this figure. Okay, now say suppose this is equal to F, this is F, then every element of f then every element of f is less than or equal to every element of E, and this implies every element of E is greater than or equal to every element of F. Now say this is my F, this is my F, this is my F. Okay, now if you observe, wait a second. Yeah, if you observe, uh, f f is a non-empty subset of S. Since E is an upper bound of f in S, this f is bounded above. This f is bounded above in S. But my assumption says S has least upper bound property. That means every non-empty subset of S which is bounded above has supremum. Therefore, now F is a non-empty subset of S which is bounded above in S. Therefore, F has supremum. Say this supremum as alpha is equal to supremum of F over S. We shall show that this alpha is equal to infimum of E over S. It's my claim to show that this alpha is also a infimum of E over S. Now we got alpha as a supremum of F. That's the greatest to lower bound. It's the greatest to lower bound of F. Greatest. Sorry. F alpha is the supremum of F. That means this alpha is the least upper bound of F. We shall show that this is the greatest lower bound of E. Now is here it says alpha is a supremum of F. Alpha is a supremum of F implies alpha is an upper bound. Of E. Alpha is an upper bound of F in S. Alpha is an upper bound of F in S. Now observe. Alpha is an upper bound of F in S, and here we observe that F is the set of here we observe that every element of E is an upper bound of F. Every element of E is an upper bound of F. Every element of E is an upper bound of F. Therefore, alpha this alpha must be uh, less alpha must be less than or equal to E for all E belongs to E. Why? See, alpha is the supremum of F over S. That means alpha is an upper bound of F in S. Alpha is an upper bound of F in S. Now, this implies every element of E is an upper bound of F. Every element of E is an upper bound of F. Now, this implies alpha is a supremum, so alpha must be the least upper bound. This implies alpha is less than or equal to E for all E belongs to E. Now, observe alpha is less than or equal to E for all E belongs to E implies my alpha is the lower bound of E in S. So it says we need to show alpha is an infimum of E, that to show that alpha is the greatest lower bound of E. Now alpha is the lower bound of E. Now suppose let beta be any lower bound of E in S. Beta be any lower bound of E in S. Now we know that from this definition, F is the set of all lower bound of E in S. F is the set of all lower bound of E in S. Therefore, this beta must belongs to F. Now what do you know about S alpha? Alpha is the supremum of F. Alpha is the supremum of F, and beta is an element of F. Alpha is a supremum of F. Alpha is the supremum of F, and beta is an element of F. Therefore, beta must be less than or equal to alpha. Since alpha is a supremum of F and beta is an element of F, alpha must be less than or equal to F. Now we got alpha is a lower bound of E in S, and for any beta be a lower bound of E in S, alpha is greater than or equal to beta, greater than or equal to beta. Therefore, alpha is greatest lower bound, greatest lower bound, greatest lower bound. This implies alpha is equal to infimum of E over S, E over S. Therefore E has supremum. Therefore E has infimum. Sorry, E has infimum. Therefore, now here E is an arbitrary non-empty subset of S which is bounded below. Therefore, every non-empty subset of S which is bounded below in S has infimum in S, which implies my S has greatest lower bound property, greatest lower bound property. Now assumed in the corners part. So we have assumed LUBP and we proved GLBP. Now we shall assume that my S has greatest lower bound property, and we shall prove that it has least upper bound property. Now the proof is similar, that is assume S has greatest lower bound property. S has greatest lower bound property means every subset of S, every non-empty subset of S which is bounded below has infimum. To show S has least upper bound property, we shall show that every subset of S which is bounded above has infimum. Let E be a subset of S. E be a non-empty subset of S which is bounded above. Which is bounded above in S. So we shall show that this by showing this E has supremum, we get that every non-empty subset of S which is bounded above has supremum, implies S as least upper bound property. Now say let F be the set of all. Okay, it's okay to take F. So say let's take G. No, we should don't not confusing with the above part, because we have already chosen F as the set of all lower bounds. Now G is the set of all. G is the set of all upper bounds of G is the set of all upper bounds of E in yes. Now think in this way. Now this is my E. This is my E which is bounded above. I don't know. Say there are some elements which is greater than every element of E. Now this is my G. This is my G. Okay. Now G is the set of all upper bounds of E in S. Therefore, clearly G is not equal to empty. G is not equal to empty, because since E is upper bounded above, there if G is equal to empty, that means E has no upper bounds. So it will contradict my assumption that but it's bounded above. It is bounded above. Therefore, G is not equal to empty. So since G has set of all upper bounds for any G belongs to G, G must be greater than or equal to E for all E belongs to E. This implies that is for any G belongs to G, G is an upper bound, therefore G must be greater than or equal to every element of E. Now for a particular if I take any element of G, it is an upper bound of E. Now by fixing this element of E, we get that E is less than or equal to G for any E belongs to E, for any E belongs to E is less than or equal to G for all G belongs to G. This implies every element of G is an every element of G. Okay, sorry. For all G belongs, this implies every element of E is a lower bound of G. Every element of E is a lower bound of G. This implies E is an lower bound of E, lower bound of E. Every element of E is G. Every element of E is a lower bound of G in yes. E in yes. Now, if you observe, G is a subset of yes. G is a subset of yes. It's a non-empty subset of yes. It's a non-empty subset of n, and just G has lower bounds. G has lower bounds. G has lower bounds. Lower bounds. And in yes, and we assumed that S has GLUBP, that is every non-empty subset of yes which is bounded below as infimum. Therefore G has infimum. G has infimum. G has infimum in yes. G has infimum in yes. Say beta is equal to infimum of G over S. G has infimum. Say beta is equal to infimum of G over S. G over S. We shall show that this beta itself is a supremum of E over S. E over S, because our aim is to show that E has supremum. E has supremum. Now, beta is an infimum of G. Beta is an infimum of G implies beta is a lower bound. Is a lower bound of G. Beta is a lower bound of G. Beta is a lower bound of G. And note that every element of E is a lower bound of E. Every element of E is a lower bound of E. And here beta is a lower bound of E. Moreover, beta is the greatest lower bound of E. Therefore, beta must be greater than or equal to E for all E belongs to E. Okay, repeat. We observe that every element of E is a lower bound of G, and beta is the greatest lower bound of G. Therefore, E must be less than or equal to beta for all E belongs to E. Now, this implies beta is an upper bound. Beta is an upper bound of E. Beta is an upper bound of E. Now, if say alpha, we shall take up. If alpha is any upper bound, of E in yes. If alpha is any upper bound of E in yes. Alpha is any upper bound of E. Now note that G is the set of all upper bounds. G is the set of all upper bound of E in yes. G is the set of all upper bound of E in yes. This implies alpha belongs to G. Alpha belongs to G. Now alpha belongs to G, and moreover, what is beta? Beta is infimum of G. That means beta is less than every element of G, and alpha is an element of G. Therefore, beta is less than or equal to alpha for all. Okay. There's a mistake. Beta is infimum of G. Therefore, beta is less than or equal to every element of G, and alpha is an upper bound of E. One second. Yes, alpha is an upper bound of E in S. Alpha is any upper bound of E in S. This implies alpha belongs to G. Now, since beta is a lower bound, beta must be less than or equal to alpha. Beta is a less than or equal to alpha. Beta is less than or equal to alpha. Now observe, what is beta? Beta is a low upper bound of E and alpha is any upper bound of E. This implies beta is less than or equal to alpha. This implies beta is less than or equal to every upper bound of E, which implies beta is a least upper bound. Least upper bound. Therefore, the upper bound of E in yes. Therefore, my E has supremum. E has supremum. E has supremum. Therefore, every non-empty subset of yes which is bounded above has supremum in yes. Therefore, S has least upper bound property. S has least upper bound property. Hence the result. Thank you.